So let's recapitulate what we did in the last lecture. We were trying to examine whether a non-zero lambda can be a spectrum. We were investigating whether a non-zero lambda can be in the spectrum of the Volterra operator. And we were looking at the surjectivity of t minus lambda I, where lambda not equal to 0. So we take an element G in L2 and we are trying to solve the equation t minus lambda I of f equal to G. So first we assume that G is a smooth function and we differentiate this and we get a first order differential equation and we solve it and we get our f in terms of G, and we got a formula for this f. What is that formula? It's equation 7.16 that you see on this slide, namely f of x equal to minus gx upon lambda minus 1 upon lambda square integral 0 to x gt e to the power x minus t over lambda dt. So if G is smooth, then we certainly know that it is in the range. We want to show that every L2 function is in the range. So let us assume that G is not necessarily smooth but merely in L2. Then the derivation of 7.16 is not correct, because 7.16 has been obtained under the stipulation that G is smooth. We differentiated the equation and we got an ordinary differential equation that we solved by the method of variation of parameters. But now what I suggest is that we take this formula 7.16, we take the f of x given by this formula 7.16 and directly substitute into the equation t minus lambda I f, and we check whether we get G. In other words, although 7.16 was arrived at under the stipulation that G is smooth, we show that nevertheless it is going to satisfy the equation. The expression f of x given by 7.16 does indeed satisfy t minus lambda I f equal to G, and that will prove the surjectivity of the function. So how do we check that this works? We have to take this expression f of x and we have to substitute in Tf minus lambda f equal to G. So now what is Tf? Tf is the Volterra operator. It is integral 0 to y f of x dx, that will be of Tf of y. So let's do that. So let us now integrate 7.16. So Tf of y equal to minus 1 upon lambda integral 0 to y gx dx minus 1 upon lambda squared integral 0 to y dx integral 0 to x gt into e to the power x minus t by lambda dt. Simply integrate the expression 7.16 from 0 to y. That's exactly what I have done. Now in this double integral, you switch the order of integration and we get Tf of y equal to minus 1 upon lambda integral 0 to y gx dx minus 1 upon lambda squared integral 0 to y gt dt integral from t to y e to the power x minus t by lambda dx. This switching of the order of integration, the limits will change. You must draw a picture and you must verify it, and I leave this verification for you to do. So now the inner integral can be computed explicitly, and so evaluating the inner integral, we will see that the expression tremendously simplifies. It will be Tf of y equal to minus 1 upon lambda integral 0 to y g of t into e to the power x minus t by lambda dt. Okay, so now we see at once using 7.16 that Tf of y minus lambda f of y equal to gy. So we see that again if we use 7.16, we will simply get exactly this equation Tf of y minus lambda f of y equal to g of y using the last display in this slide. So we have proved that any non-zero lambda cannot be in the spectrum of the Volterra operator. So this completes the verification that t minus lambda I is surjective if lambda is not equal to 0. In general, if you take any bounded linear operator on a Hilbert space, the spectrum is always going to be non-empty. This is a very important result in functional analysis, and you can consult any of the books on functional analysis such as Simmons' Topology and Modern Analysis, for instance, where you will see a proof of this result, that the spectrum of a bounded linear operator is always non-empty. It must contain at least one element, but the Voltaire operator shows that it can be as small as it possibly can, namely it can be a singleton. 0 is in the spectrum, 0 will always be in the spectrum of any compact operator, and Voltaire operator is a compact operator. However, this kind of pathology will not happen when the compact operator is also self-adjoint. Remember that the Voltaire operator is not self-adjoint. It is given by a kernel, and the kernel is not a symmetric kernel. So if you have a compact self-adjoint operator on a Hilbert space, it will have many elements in the spectrum. In fact, there will be a basis of eigenfunctions. That means that the spectrum is quite rich enough to produce enough elements as eigenfunctions to span the whole Hilbert space. However, we shall need some preliminary results before we embark upon the proof of the spectral theorem. The first such result is the notion of weak convergence of a sequence. Suppose Vn is a sequence of vectors in a Hilbert space. We recall that Vn is said to converge to V in norm if norm of Vn minus V goes to 0 as n tends to infinity. This is the usual definition of convergence in a metric space. A normed linear space is a metric space. Distance between Vn and V is the same as norm of Vn minus V. So Vn converges to V in the Hilbert space norm if norm of Vn minus V goes to 0. Now, we introduce a much weaker notion, that of weakly convergent sequences. A sequence Vn of vectors in a Hilbert space H is said to converge to V weakly if the inner product of Vn with W converges to the inner product of V with W for every W in H. So now we say that V is the weak limit of the sequence Vn. We say that V is the weak limit of the sequence Vn. Now, using the Cauchy-Schwarz inequality, we see at once that norm convergence implies weak convergence. It's a simple exercise, and I leave it to you to check this. As a first example, again coming from Fourier series, let us take the classic example of a Hilbert space L2 of minus pi pi. And let us look at the sequences sin nx and cos nx. These sequences sin nx and cos nx converge to 0 weakly. Why do they converge to 0 weakly? Simply appeal to the Riemann-Lebesgue lemma. In fact, the Riemann-Lebesgue lemma asserts that these sequences go to 0 weakly. However, they don't go to 0 in norm. More generally, let us take any orthonormal sequence Bn in a separable Hilbert space. Take a separable Hilbert space such as L2 of minus pi pi, and we are taking an orthonormal sequence. So you could take these sequences sin nx or cos nx and normalize them. Now we can always complete it to an orthonormal basis. So this orthonormal basis, let us call it Bn, and this enlarged sequence itself will go to 0 weakly. How does one understand this? We have to show that for every V in H, the inner product of V with Bj goes to 0 as j goes to infinity. But remember that I had taken an orthonormal sequence and I have completed it. You take a vector V in H and write V in terms of this orthonormal sequence. Say write V as x1 b1 plus x2 b2 plus x3 b3 plus etc. So what are x1, x2, x3 etc.? They are the Fourier coefficients of V with respect to the given orthonormal basis. And what does the Percival formula tell us? The Percival formula tells us that norm V squared equal to mod x1 squared plus mod x2 squared plus mod x3 squared plus etc. And therefore, the infinite series converges, the nth term must go to 0. In other words, xn must go to 0 as n goes to infinity. In other words, the inner product of bn with v must go to 0 as n goes to infinity. And we have finished the claim that if bn is a orthonormal basis in a separable Hilbert space, then bn goes to 0 weakly. But this is very far from norm convergence, because if you take n is not equal to m, then norm of bn minus bm is exactly root 2. So, a distance between any two of these points is root 2, and so there is no hope of this sequence converging in norm. So, now that we are disposed of this preliminary, we now prove a theorem. Suppose Vn is a sequence of vectors in a Hilbert space converging weakly, then the sequence is norm bounded. In other words, weak convergence implies norm boundedness. That is, there exists a constant m such that norm of Vn less than or equal to m for all natural numbers n. Okay, that's the first part of the theorem. The second part of the theorem says that if Vn is a sequence of vectors in a Hilbert space which is norm bounded, then there is a subsequence converging weakly. It is a partial converse of 1, namely norm boundedness implies weak convergence of a subsequence. So, this is exactly the kind of compactness result. We do not have convergence in norm of a subsequence, we have weak convergence of a subsequence. So, the lack of compactness of the unit ball in an infinite dimensional space has been resurrected by using weak convergence instead of norm convergence. The proof of 1 is a nice application of the Banark-Steinhaus's theorem. So, you must go back and recall what the Banark-Steinhaus's theorem is before reading the proof of this theorem. So, for each natural number n, let Tn from h to complex numbers be the linear transformation given by Tn of w to be the inner product of w with Vn. It is evidently linear, it is complex valued. What is the mod of Tnw? Mod of Tnw by Cauchy-Schwarz is less than or equal to norm Vn into norm w. Now, we know that norm Vn is bounded and Tn of w converges for each w, that is because Vn converges weakly. So, the sequence Tn w is bounded for each w, and the bound m sub w will depend upon w. The Banark-Steinhaus's theorem says that there is a common bound, namely mod Tn w less than or equal to capital M for all natural numbers n and for all w in the closed unit ball. That is, we have uniform boundedness. So, in particular, mod of inner product w with Vn is less than or equal to capital M for all n in natural numbers. So, we simply take the w to be Vn upon norm Vn, and we immediately conclude that norm Vn is less than or equal to m for all natural numbers, and the proof of the first one is complete. To prove the second one, we are going to assume that the Hilbert space is separable. What is the meaning of saying that H is a separable Hilbert space? The next line clarifies it, namely the Hilbert space has a countable orthonormal basis, namely there is an orthonormal system B equal to B1, B2, B3, etc., such that the linear span of B is dense in H and the B1, B2, B3, etc. are mutually orthogonal unit vectors. Since Vn is norm bounded, take the inner product of Vn with B1. What is the absolute value? The absolute value of this is less than or equal to norm Vn into norm B1. Norm B1 is 1 and norm Vn is bounded. So, this scalars, the sequence of scalars inner product of Vn with B1 is bounded. So, there is a convergent subsequence. Here we are simply applying the Bolzano-Weierstrass theorem for the real numbers or complex numbers. Every bounded sequence of real or complex numbers must have a convergent subsequence. So, let us call this convergent subsequence Vn1, B1 converging to say A1. It is convenient to call this subsequence Vn1, Vn2, Vn3 as V of 1, 1, V of 1, 2, V of 1, 3. It is the first subsequence that we have produced out of the given sequence V1, V2, Vn. Now work with the subsequence. Now hit all these subsequence with B2. Take the inner product of all the elements 7.17 with B2, and what do we get? The sequence V1, Nj, B2 is bounded. And so there is a subsequence converging because it's a bounded sequence of complex numbers, namely V1, Nj, B2, and that will converge to A2. The original sequence was V11, V12, V13. We take the inner product of all of them with B2. That's a bounded sequence, so extract a convergent subsequence. So V1, N1, V1, N2, V1, N3, inner product with B2, that converges to A2. Now it is convenient to denote this new subsequence or the subsequence that we got as V21, V22, V23, the display 7.18 in the slide. Again you hit all of them with B3, that is, take the inner product of all of them with B3, we get a bounded sequence of complex numbers. Take a subsequence, let us call it V31, V32, V33, etc. And inner product with B3 goes to A3. So proceeding thus, we get a sequence of subsequences, and you simply take the diagonal sequence. What is the diagonal sequence? V11, V22, V23, etc. This diagonal sequence 7.19 has the property that after a finite stage, suppose I take the jth stage, say Vjj onwards, it will be a subsequence of the jth subsequence in our list. But we know that Vj1, Vj2, Vj3, etc., all of them taking inner product with Bj converges to Aj. So this diagonal subsequence has the property that inner product Vnn with Bj will converge for j equal to 1, 2, 3, etc. So now we must make an educated guess as to what should be the weak limit of Vnn, and then we should prove that our educated guess is indeed correct. So let us assume that the weak limit, whatever it is W, and this W is x1 b1 plus x2 b2 plus x3 b3. After all, every element in the Hilbert space can be expressed in terms of b1, b2, b3. It's an orthonormal basis. We know that Vnn inner product with Bj converges to Aj. But what happens is that we also know that Vnn with inner product with Bj is supposed to converge to W, Bj. And that forces Xj to be equal to Aj for all j. And so our educated guess for the weak limit is W equal to A1 B1 plus A2 B2 plus A3 B3, etc. So 7.20. So if at all our Vnn has a weak limit W, that W must be compulsorily be A1 B1 plus A2 B2 plus A3 B3, etc. Now we got the serious job of checking that 7.20 converges. When will a series of the form 7.20 converge? It's a Fourier series. So it will converge if and only if we are looking at the L2 setting or the Hilbert space setting. So it will converge if and only if mod A1 squared plus mod A2 squared plus mod A3 squared, etc. less than infinity. So let us verify this later. Let us verify the convergence of 7.21 later, and let's continue with the argument. So now we have to show that for every V in H, the inner product Vnn minus W with V goes to 0. That is the meaning of saying that Vnn converges to W weakly. Now this clearly holds when V equal to B1, B2, B3, etc. It's completely trivial, it's by definition. And therefore, the assertion must hold for every P in the linear span of B. So whenever V happens to be in the linear span of B, Vnn minus V, inner product with V will go to 0. So now we have to go from the linear span of B to the whole space. The linear span of B is dense in the whole space. B, remember, is a basis. So it's a set of all finite linear combinations of elements of B are dense in our Hilbert space. So take an element V in our Hilbert space and let epsilon greater than 0 be arbitrary. By denseness, there is an element P in the linear span of B such that norm of V minus P less than epsilon by 2m, where m is a convenient bound. Say take any m which exceeds norm Vn plus norm W. Remember that our norm Vn are bounded. Also for this P, there exists an n naught such that Vnn minus W inner product with P less than epsilon by 2 for all n greater than n naught, because we know the convergence to 0 for this particular P. So for n bigger than n naught, we must add and subtract a P. So inner product Vnn minus W with V, add and subtract a P, we get inner product of Vnn minus W inner product with P plus Vnn minus W into inner product with V minus P. For the second part, use Cauchy-Schwarz inequality. It's norm of P minus V into norm of Vnn plus norm W. Norm Vnn plus norm W is less than m, and norm P minus V is less than epsilon by 2m. So all in all, it's less than epsilon, and we have proved that Vnn indeed converges to W weakly. And that completes the argument. All that remains is to prove 7.21, namely that the series mod a1 squared plus mod a2 squared plus etc. plus mod an squared converges. So let's prove this. Let's prove this 7.21. It's a nice application of the parallelogram law. What is the parallelogram law? In a Hilbert space, if V and W are two vectors, norm V plus W squared plus norm V minus W squared is twice norm V squared plus twice norm W squared. So first let us fix a capital N and let us look at 7.22, norm of Vnn minus twice a1 b1 plus a2 b2 plus etc. plus an bn the whole squared, and let us expand this. Let us expand this. We get norm Vnn squared plus 4 times norm of a1 b1 plus a2 b2 plus etc. plus an bn squared minus 4 times inner product Vnn with a1 b1 plus a2 b2 plus etc. plus an bn. Now Vnn dot with b1 goes to a1, Vnn dot with b2 goes to a2, etc. And so the last two terms in second equation in the display together goes to 0. And we conclude that the expression 7.22 is bounded. So now let us apply the parallelogram law with x equal to Vnn minus a1 b1 plus a2 b2 plus an bn, and take y to be a1 b1 plus a2 b2 plus an bn itself. So x minus y is norm bounded. That's exactly what we have just shown. 7.22 is x minus y. And so now we have capital X plus capital Y norm squared plus capital X minus capital Y norm squared is twice norm capital X squared plus norm capital Y squared, which means that twice norm capital Y squared less than or equal to norm x plus y squared, which is norm Vnn squared plus norm of x minus y the whole squared, which we have just shown is bounded. So norm y squared is bounded. In other words, what is the norm y squared? Norm y squared is mod a1 squared plus mod a2 squared plus etc. plus mod an squared. We have shown that mod a1 squared plus mod a2 squared plus plus mod an squared is bounded by some fixed number a, and the proof is complete. Now you see, the proof of this part was very long. The reason why it was very long is because it was elementary. We did not use any high-powered machinery from functional analysis. We tried to prove it from scratch, and we were able to do it because we are in the Hilbert space setting of a separable Hilbert space. If we permit ourselves the use of some sophisticated theorems from functional analysis, the proof will be much shorter. In fact, the proof will be a one-liner. It follows from a general result called the Banark-Alaoglu theorem, and the Banark-Alaoglu theorem says that the closed unit ball in the dual space is weak star compact. So it requires a lot of preparation. We'll have to look at the weak star topology, we'll have to look at the dual space and so on and so forth. Unfortunately, in this elementary course, we cannot develop this machinery. It will take us too far afield. But if your curiosity has been aroused, you must, and I recommend that you do, consult, for instance, Goffman and Pedrick, page number 210. It's a very good book on functional analysis. However, I must tell you that in this book, Goffman and Pedrick do not call it the Banark-Alaoglu theorem. They prove the theorem, all right, but they don't call it the Banark-Alaoglu theorem. And note that the main thrust in this argument is that the closed unit ball in an infinite dimensional space is not compact in the norm topology. And so norm boundedness doesn't imply norm convergence of a subsequence. All we have proved is that we have a weakly convergent subsequence. Instead of a norm convergent subsequence, we have a weakly convergent subsequence. In other words, we have a convenient substitute for the absence of the compactness of the unit ball in an infinite dimensional Hilbert space.